Yep. Hi. Thank you for having me. I'm Keisuke Nishimura, and I'm from INRIA, the National Institute in France, about information and computer science. And today I will talk about our work about the verification for the Linux kernel itself. So here is the outline of today's talk. First, I think there are a lot of people from different backgrounds. So let me give you a brief introduction for verification, and then I will demonstrate a simple example for of verification for a small function for the is-core idle. And finally, I will see some practical challenges for the verification of the Linux kernel. So let's get started. But let me start with the background, obvious background. In theory, the operating system should always run properly, but in reality, we have a lot of bugs. It's hard to avoid. Some bug follows some typical patterns like pointer reference, and there are many tools to detect such bugs. But the other class of bugs, such as semantic bugs, it's very hard to detect such bugs. That's why verification. Here is the overview of the deductive program verification. It takes specifications and program, then the verifier decides if the specification is a program, the implementation. So what is specification? Here, I want to define the correctness of the verifier using core triple. But it's very simple. As specifications, we assume precondition and postcondition, which means that if this precondition holds, then after the execution of program, this postcondition holds. That's it. So here's an example. It's very stupid, very simple example. Here, it says that if x is more than 1, then after this execution, it should be more than 2. But also, we can say that x is more than minus 10, for example, because it always holds. That's the specification. And the verifier takes programs and specification. Then it translates into logical formulas called verification condition, VC. The verification condition holds. This means that the program is correct. Here, first I need to say that we need to annotate loops with invariants. I will discuss it later. And also, the verifier translates programs and specification to logical formulas. Then we need to somehow discharge the logical formulas called verification conditions. There are some available options. But first, let's see what's the verification conditions. The simple idea to generate verification condition is to find the weakest preconditions by reasoning in the backward direction. For example, in this case, to hold the post condition, the weakest precondition is x is more than minus 1. Then the verification condition is here. The weakest precondition implies the given precondition. So it's very easy. We can somehow automatically generate this kind of verifications. However, if we encounter a loop, then it's very hard to do that because we don't know how many iterations can happen in advance before the execution, and maybe the loop is infinite. So in general, there is no way to automatically finding a good condition or a good logical formula for the verification. We don't have a general solution for this. That's why we need to annotate loops with invariants. Invariants conditions of logical formula, or we can say conditions that holds before and after the loop body. Then using this invariant, we can generate verification condition. That's why we need to annotate manually. We need to annotate loops by hand, and then the purpose is to generate verification conditions. Here is an example of loops and its verification. In this loop, it initializes an array with 0. In this invariant, so this invariant says that for all integer j, if the j is in this range, then a of j is already initialized with 0. And also, I moves from 0 to 10. This holds before the execution of the loop body, and after the execution of the loop body, it also holds. That's why it works as a loop invariant. And yeah, again, it's important generally. It's important to finding such constraint for any kind of loop. So it can be a major stumbling block to apply a verification to the Linux kernel or any other software. However, for practical verification, we need some degrees of automation. Now our research team is trying to automate this process to a certain extent. We will see it later. Yes, and so far we talked about what's the verification condition and loop invariant. Then we need to somehow discharge the verification condition. There are some ways to handle this kind of logical formulas. First one is pen and paper proof, but we don't like it. So maybe the second approach is to use interactive theorem provers. It sounds a bit overwhelming, but it's just a mathematical system to write your proof. You need to write proof, but you can verify a lot of things by yourself. But you need to put a lot of effort. The other approach is to use SMT solvers, which is automatically trying to solve this kind of equation or logical formulas. But there's no guarantee of success. We have two options to discharge verification conditions. In that sense, we have some design spaces about the verifiers, and of course there are a lot of implementation of available verifiers. But in this talk and our research group uses Pharmacy. The reason is, the one biggest reason is that Pharmacy is very mature. It provides a very good software ecosystem, and also it uses SMT solvers to automate discharging verification condition, and also it allows for explicit specifications. So let's see how to use Pharmacy to verify actual function in the Linux kernel is for idle. And as the name shows, is for idle is used in a task scheduler in the Linux kernel. And let me give you a brief background of this function to define its specification. In the task scheduler of the Linux kernel, they try to move a task from busy CPU to an idle CPU, and a destination CPU should be in the core that is also idle, which means that all CPUs belongs to so the all CPUs in a core should also be idle. The function is core idle is to check whether the core to which a destination CPU belongs is idle or not. And here the implementation of is core idle. It takes CPU ID and then return true if and only if the core is idle. So you can see for loop for each CPU. It's actually a usual for loop, of course, and in this for loop, it iterates over CPU IDs in a CPU mask, which is a set of CPUs. And once non-idle CPU is found, then it can it returns false immediately. And if all CPUs are idle, then it returns true. So here's the case where CPU 1 is non-idle. Then in this loop, it finds non-idle CPU, then it returns false. But if there's no non-idle CPUs in the core, then it can return true. Here, this return statement is triggered. So we want to apply verification for this function. But before directly providing the specifications and loop invariant, what we need to do first is to model CPU states. Here's an example of the states of CPU. The CPUs have the property of idleness. So let's use this predicate to describe the property of idleness. For example, CPU1 has an idle, so CPU1 has a task, then it's not idle. But CPU3 is idle, something like that. Of course, we don't need to give an actual definition of idle CPU. It serves as just a predicate. And also, I introduce this function getCore as logic function, which is a function just for specification. Not C program cannot invoke this function. This function maps CPU ID to a core ID in this case. For example, getCore of 0 returns 0, and getCore of 3 also returns 0, because the two CPU belong to the core 0. And the getCore of 0 is different from getCore of 4, because the core is different. So here is the environment that we want to use to define the specification of this function. Here, here's the core predicate that relates that give relationships between idle core and idle CPU and getCore. In this predicate, it says that if the if a CPU I belongs to the same core of CPU, then such CPU must be idle. We can write this kind of specification to describe the situation in CPUs and CPU topologies and CPU or tasks properties. Then we need to define the dependencies. Yes, we have something to do to verify the function itself. Here, it defines the function called idle CPU. This is called in the function isCore idle. Then it maps to the here we define precondition using requires. This is a keyword for pharmacy, which is a verifier we are using. And also it maps the result to the idle CPU, the predicate we already defined. This is very somewhat simple. Simple definition of specifications. And also it says that this has no side effect in this function. Another function is a bit tricky, so I don't want to go to the details, but it just says that this function returns a CPU mask that represents the CPU set contained in the core, where the CPU belongs to. So it means that the CPU here is included the return value, the returned CPU mask, and also the other cores share the same. So other CPUs sharing the same core are also included. Yeah, it might be a bit tricky definition, but somehow we can define a bit tricky specification. So finally, we can define the specification for the function, for this function. The specification itself is very simple. The result is corresponding to the result of idle core we defined first. And also, maybe we can notice that this function assumes that the parameter CPU, the parameter of CPU is also idle. It's not written in the code directly, but it assumes. And finally, we need to write a loop invariant. We need to do a lot of things. Here, this loop iterates over the CPU IDs in the given core and skip idleness check. Here, yes, I can see the mouse one. Yes, skip the idleness check for the given CPU, and otherwise it checks the idleness. And we can somehow come up with an idle. Sorry, we can somehow come up with this loop invariant. Here it says that CPU, if CPU J is in the CPU mask, then it should be idle. That's all. Then we can verify if we can run from a C with such definitions and code and loop invariant and specification. Then the Pramacy says, oh, this function is correct or this function meets the specifications. But for the specification part, I think we need to consider what's the specification is. But for the loop invariant, we want to somehow automate to infer these kind of things. This kind of logical formulas. So finally, let me introduce some our works about practical verification for the Linux kernel. So we hope somehow automate the inference of loop invariant for the Linux kernel. There's no general solution, but adapting to the Linux kernel may allow for a practical solution to a certain extent. Our insight is that there are idiomatic usage patterns in the Linux kernels. I mean, for example, for CPU, this is a somewhat famous macros because it used more than 400 loop instances in the code. It performs a similar operation in a loop body to a certain extent. Then by capturing this kind of behaviors, and we are thinking that automate the generation of loop invariants. So this is our current work. And also, in the general view, here is a workflow of the ideal verification of the Linux kernel, and we select a function of interest, then write a specification. But it's not that easy to write a specification. Why? So because we need to answer a very simple question: what input of a verifier should be? One can say that since the Linux kernel is written in C, then the C file can be an input. Then by adding a specification to C code in the Linux code base, then we can directly, then from a C can take it as an input. Yes, it's possible, but it contains a lot of irrelevant code. And also there are many other dependencies. So many dependencies located in other files. And also for example, if you want to verify the correctness of scheduler, then probably you don't so much care about printf or PL info or debug assertions or something like that. Sometimes those kind of informations can hinder the verification itself. The print k, for example, print k is very complicated function, but we don't want to touch it for the correctness of scheduler, for example. Then our solution is to automatic preparation of verification code. Our idea is to extract target functions and dependencies into a minimum but self-contained compilable file instead of the very large C file in the Linux code base. And then we replace dependencies like types and macros with ones suitable for verification based on user instructions. We are now developing this. So we are working on the development of this preparation tools, and we hope that in the future we will make it publicly available. And let me show you an example about the usage of the tools. For example, in the case of its core idle, which is defined in kernel/sketch/clear.c. For example, clear.c is a very large C file. It contains more than 13,000 lines of code. And after the macro expansion, it becomes 100,000 lines of code. We don't want to manually manage this big code. So instead, we can extract essential part from the clear.c. It becomes 66 lines of code. It contains 9 macros and calls and type definitions, etc., etc. And those dependencies are declared or defined across 10 other files. So manually preparing such dependencies is a bit time consuming and error prone. That's why we are trying to automate this process. Yep, finally, let me show you some other challenges toward the practical usage. The first of all, actually I think this is very important part. We don't have a formalized specifications for the Linux kernel. We want to verify the function. We want to somehow verify the Linux kernel Linux functions, but it surely it has some comments, or we know the general high-level architecture of some components in the Linux kernel, but it's not formal, so it's very hard to find the correct specifications for the target functions, and the correctness always depends on the context and situation. And also, I introduced some idea of SMT solvers, and I said it's automated, but actually, so the automation means that it's very hard to guide them. Even if specification is correct and even if the program meets the specification, it doesn't mean that SMT solver can find it correct, find it valid. So there are a lot of researches here, and we are trying to somehow do better. So here is the summary. First, I introduced a quick introduction of deductive program verification. Here, the specification is defined as pre and post conditions, and we need loop invariant. We need a manual annotation of loops, and also we can somehow automate discharging them using SMT solvers. for towards practical application of the verification, now we are trying to automate the preparation of verification and also inference of loop invariants. And also finally, the good specifications and better automation is still, we need a lot of rooms to improve. So that's all. That's all my, this is the last slide. Thank you. Do we have any questions? Go for it.
So I guess when you prepare your specification, right? So these are formal models. In general, very complex. So the point is, you should start from a piece of code. Let's assume there is a plan. So when you create specification automatically, I mean, are the specification created automatically or by human in this context?
The specification, in principle, specification. So a human, a user needs to provide specifications, but in reality, there are a lot of auxiliary functions in the Linux kernel. For those functions, I think automatic inference of specification can be helpful. But I agree with the point. To my understanding, your point is that if a bug is contained in current implementation, then if we automate automatically infer, then
so my concern is that, I mean, at the end of the day, you can create the specification, or maybe automatically, but then there is the risk that you don't, I mean, you don't know if there is a bug or a feature unless you have a subject matter expert who is looking at the specification and say, oh yeah, this is the intent of this function.
yeah.
I think so. So I was just wondering, like, how, I mean, all these, how, I mean, practically speaking, how it can scale, because I mean, this is here you're mentioning like practical application.
Actually, I have no clear answer to tackle this problem. Yeah, for example, if developers write the specification first and implement it, then we can say that specification is correct. But it doesn't happen.
No, we can't.
Yeah, of course.
We cannot.
Yeah.
It's specification and the source code, two different things.
Yes.
If you write specification, it does not mean that the code is correct.
But code should meet the specifications.
Yeah, but you can write the cases according to the specification.
Yeah, but this is modern, modern specification. What you try to do, you have 66 like lines of code, right? So and you try manually to create a specification, like and you need then something which verifies that your specification is correct,
Yeah.
And how you would do this, like no one would create a specification for you. They just write in the source code,
Yeah. Yeah. Sure. We don't know. Yeah. Sometimes we can ask if your intention is the specification our specification captures your intention or not to a developer in theory, but it doesn't mean that so it doesn't scale. So yeah, the correctness of specification is very big problem. In this case, for example, I think this function is somewhat small, so somehow everyone can investigate the specifications and can somehow manage this level of specification. But if we verify a very big component, then maybe the specification can be very big. So how to maintain the correctness of specification is still we have no clear answers.
Another question that I may have. You said in one of your passage that you are resolving macros inside the thing. Is this correct? Because the kernel code, not this one, but most of the kernel code depends on configuration.
Yes.
So you also need a configuration in order to analyze any particular function. Then, since I'm keen on this part, there is another problem, which is you are dealing with the source code.
Yes.
But what actually run into the machine is not the source code, but is a binary code.
Yeah.
And you have also to account that compiler not always do what you suggest to do with your source code. So in the end, you may arrive to prove something that is not what actually run on the machine. Is this anyhow accounted into the work?
Yeah, exactly. So the translation also needs to be somehow validated. Yeah, of course, the applying verification might be the best, but practically, it should be somehow validated. And also, in the case of macros, actually, the preparation stick to our tool stick to one configuration, and it cannot handle like two configuration or other architecture or something like that. Yeah, so this is my limitation of our tools.
For example,
Okay,
We need to.
yeah, I think we're going to continue this into the hallway track afterwards. It's the right topic for all of us to talk about, including my questions, but I'd like to get the next speaker up so that we could keep ourselves on track. Thank you so much.
Thank you.
Philip, okay, this is Ming. Can you assign me co-host?
I'll do it. It's fine. We need to stop recording anyhow.